Good evening, everyone. Great to see many people attending the webinar today. Welcome to Quantum London. We have a couple of exciting speakers today, which will tell us a bit about their story in the quantum computing world. Marco and Paul, I will hand over to them in a second. But before we get started, I just wanted to, again, welcome everyone and maybe introduce very briefly what is Quantum London and what we do, what we are trying to achieve. So this is born from an idea of Paolo, who is in the background and will take over in the second phase of the webinar. The idea behind all of this is to try and anticipate what the business impacts of quantum computing will be from mainly a business point of view. So what will be the use cases? We all know this is coming. We know it's going to make a huge difference in some areas, but what are these areas? What are the use cases which will be more relevant? So what we try to do is both build a community of people who share the same interest around these topics, and we started with more questions than answers, and then we figure out, well, if we want to have some answers, we want to talk with the experts. So we started bringing in experts like the ones we have today to help us understand a bit more about what's happening, when it is coming, what kind of changes will bring in to us. Without any further ado, we have a quite packed agenda. I will hand over to Paul and Marco, so can they do a bit of introduction about themselves, and then we have quite an interesting journey around what has been their what they've done in the field, and they will help us understand a bit more about the question, the topic for today. A couple of good order points. So the meeting is being recorded, just for your awareness, and we will be taking questions through the chat. There will be a Q&A sessions toward the end, so please feel to put your questions in the chat, and we will ask Paul and Marco the questions towards the end. Myself and Paolo will help through the chat to moderate the questions. I think that's me done, and over to you, Paolo and Marco.
Hi everyone. My name is Marco Paini, and I currently work for Rigetti Computing, and I'll talk a little bit about what we do as I start talking about quantum computing. I've joined Rigetti about a year ago as the result of the acquisition of QxBranch, and we'll cover that too as we go along, what QxBranch did. And I've been with QxBranch for a little bit more than a year. Before the acquisition. Before then, I've actually spent most of my professional career in technology consulting. I was working for a technology consulting firm, Accenture in particular. I studied physics before starting to work for Accenture, and I sort of came back full circle, trying to combine a little bit of what I've gone through with Accenture in terms of, again, consulting and focusing on business value, and a little bit of an understanding of quantum mechanics and quantum computation. I happened to actually do work at the time of my thesis on stuff that, even if we weren't talking about quantum computing, was actually pretty close in terms of mathematical framework to actually what's used in quantum computing now. So that's myself, and Paul, over to you.
Yeah, absolutely. So Paul Guthrie, I currently manage a company called Enveloprisk. Enveloprisk does a number of things. Our shop window is that we're a cyber reinsurance agency. We built some of the core technology there with some of the individuals from QxBranch originally, who have expertise in simulation modeling and artificial intelligence. We look very closely at the cyber environment, and we use that to price cyber insurance and cyber reinsurance products and do a number of pieces of work around there. Previously to that, I was a co-founder of QxBranch, spent about 5 years building that business. We got to work with a number of firms in a number of different verticals, obviously insurance, a number of investment banks, oil and gas, pharmaceuticals, aerospace. We looked at a large number of problems and how they might be solved, developed some hardware roadmaps, some software roadmaps, spent a lot of time trying to really characterize what is the future of quantum computing and how do we really position for it. Before that, there's another fitness company that I've started that I'll kind of set aside. It's not directly relevant to this. Prior to QxBranch, I spent about 10 years working mostly for NASA and the US military on technology strategy. So that was all around how do you take new technologies and how do you get them in the field or in space as fast as possible at low or no risk. And so a lot of the R&D procedures that we used to use there, a lot of the horizon scanning tactics that we used to use, a lot of the forecasting that we used to use regularly, all of that stuff becomes very relevant when you start taking a very complex and very high impact technology like quantum computing and begin to think about not only what can it do, but how do we think about being prepared for that and merging it into our organizations and using it to gain a real commercial advantage there. My background is not in physics. I'm sort of a bad economist. I have a degree in economics, a degree in policy, science and technology policy. And then my background is philosophy from way back. So between philosophy and physics, Marco, me and you should be able to cover any type of cognitive strategy that anyone wants to use to ask questions. So I think in the purpose of this conversation is to give you guys a very broad view of what is happening in this industry, to help you understand what the timeline is, obviously a little bit about the hardware. We don't want to get too technical into it. And then we can start to talk about some of the classes of problems that it can really solve. I think one interesting thing for everybody in the crowd to think of is that this is a new technology and it's quite an impactful technology. It's going to make, when it works orders of magnitude better than the technology that it's replacing. So that means a couple different things. One is that you're uncovering problems that you're already kind of solving, but you're solving it in a different way that's not as good. Or you're uncovering problems that you've just never even tried to solve because the way quantum computers work is just so inconceivable that you would ever try to solve a problem that way that you just kind of put it aside and you're like, oh, that's something that computers can't really do. And relatedly to that, the advantages that come out of quantum computing, because they're so substantial, are often kept quite secretive. So when different firms have come across strategies that they want to take to positioning for this, they don't run around saying, hey, we've discovered this great new trading signal and it's going to take 4 years to develop. What they do is they shut up and they start developing the software and they start preparing for the time when that's actually really going to work. And then the final thing, which I hope is exciting rather than disappointing, is that this is very much a technology, which is an obvious thing to say. But the significance of that is that this is a capability. It is a capability that's getting developed because we know that it has a huge amount of power. It's up to you guys in the audience, and it's up to the users of this in the future to figure out, all right, if we have this capability, what are the problems that we can really solve? So we, Marco and me, we have some ideas around here, some problems that people have solved in the past. But for the most part, because this is new and because it's a capability, we're very much taking a technology push / supply side approach to this is what we can do. And everyone in the audience, this is such a new technology still that equipping yourselves at this early stage to understand what it can do and how to think about it differently positions you pretty well to be thoughtful in the future and identify what are the use cases and really play a leadership role in implementing some of these within your own organizations.
Thank you. Thanks. So maybe can we start from there? Can you give us a very brief explanation of what quantum computing is? Let's keep it brief. I think most people might be familiar with it if they're in this group. And then maybe start covering some of those, what is the business problems, categories of business problems which are being solved by quantum computing. Why is this important? Then are there any particular industries which will be most impacted by these technologies? Marco, I think you might be on mute. Yes, please. Yeah.
Fashion, we've got to have slides. Let me do that. If I can make. Yeah.
Here, Marco, while we pull this up and say that, I'm sure everyone on this call knows this, but the idea quantum computing, it's It's literally what it is. So what it's not a brand name, it's not a buzzword. What quantum computing is it's taking advantage of quantum effects to make calculations. And nobody really understands what happens in the quantum world is very non-intuitive. So even the best quantum physicists in the world will readily say, I have no idea how quantum physics works. And so any intelligent person who's not a quantum physicist, you should be very comfortable mirroring that and saying, I also don't really understand how this works. It kind of gets at the fundamentals of the structure of the universe, and it can get into things like parallel universes and all these wacky things, but we're not going to go that far. But the fundamental thing that you're thinking about when you're thinking about quantum computing is, how do we take advantage of the weird, spooky behavior of subatomic particles, and how do we use that for information theory? I guess the last piece I'll just say, these were first theorized. I'm sorry, Marco. These were
go ahead.
Yeah, these were first theorized in about 1980. So it was in 1980 that the first individual was like, oh, you know what? I bet you could use this for computing. And then the first algorithms were kind of developed in the 80s as well, saying if we had a computer, we could break encryption. And here's the algorithm that we could actually use to do it. And it wasn't really until the 90s and the early 2000s that people started actually building hardware that seemed to work. And then it wasn't again until the 20 teens, and this was early, this was much faster than most forecasts, that people started building computers that they thought they could do some significant research with, or maybe even start to build a commercial industry around. So commercial industry has really emerged since around 2011, 2012. And it's picked up a lot of steam and has a lot of investment and a lot of momentum now, both on the commercial and the government side. So that's the background.
Yeah, so that's a great summary. In fact, I think the easiest, and I'm just maybe again going to show a couple of slides to sort of repeat the concept that Paul had explained. I will not try to explain what a qubit is and superposition, all of that. And some of you might have seen slides, and actually some of you might be in the field. I think that doesn't really tell the story as to why quantum computers have a greater computational power. The truth is, as Paul said, there are the laws of physics at the microscopic scale are different from those at the macroscopic scale, so at our scale. And that difference is what we try to exploit by controlling a system at the microscopic level to do things that we are limited in because of simply how things work at our scale. And typically, one way to consider what quantum computing as a technology is useful for is starting from high performance computing. And that is because quantum computing ultimately is supposed to be used for difficult computational problems. We've come a long way in a few decades from like the initial rudimentary computers to what we have now. I actually had this slide I think I created this slide in May, and I've realized while I was sort of reviewing it that in May, this was IBM Summit was the fastest computer in the world. And only in a couple of months, it is no longer the fastest computer. There's one now in Japan, which makes this machine that you see here in the picture the second fastest right now. So you have impressive specs and performances. There are reasons, though, for which we believe that we are not going to be able to continue to make progress as we've done in the last decades and do exponentially better with these machines in the future. Regardless, even if we were able to continue progress, there are problems, and as Paul said, that are difficult. And in particular, any problem that has to do with a description of a microscopic system, we believe that is difficult on a classical system, and pretty much no matter how big your classical system is. And this is the idea that Paul was referring to, in fact, from the early 80s. So why don't we think about then using a microscopic system, controlling it to then describe another microscopic system. So this is the idea behind quantum computers and the fact that it really is a quantum. It refers to quantum mechanics that describes these microscopic systems. It turned out that the sort of operations that we could do, at least in principle, on a quantum computer, they would have been helpful to describe microscopic systems, but actually not only that, there are some other computational problems completely unrelated, for which the same techniques would have actually led to a result that classically, with classical methods, would have been fundamentally possible, at least for the algorithms that we know now. And so the classical example is Shor's algorithm from 1994. This is probably one of the most famous algorithms in quantum computing, which allows the factorization of a composite number in its 2 primes. Its relevancy is that the technique of actually, so the difficulty around factorization of a composite number is the principle behind most of today's encryption. And so it is being able to find factors efficiently is a problem that has, the great relevance, just beyond the mathematical interest. There are, of course, many more algorithms, and there are categories and of fundamental mathematical ones and actually more practical ones that have been developed. And I think the effort on algorithms has been as intense over the last years as the hardware effort. Now, the last thing I'm going to show, because I suppose often we talk about quantum computers, and there's that leaves a doubt as to what these machines look like. So I've got a picture of some Rigetti's computers, which is this, so Rigetti, the company I currently work for, manufactures the components that go in quantum computer, assembles quantum computers, and offers them on the software stack, and offers access through the cloud. So a quantum computer is fundamentally one of these white cylinders with some control, so all the electronics that you see outside. So these are about 1.5 or so meters high, and this is our facility where we're hosting them in Berkeley. Now, I've been talking about a microscopic system, and this thing looks anything but microscopic. Now, so another picture that sort of shows what the quantum computer is, that's something that shows what's inside the cylinder. And inside the cylinder, it sort of looks like this. And I won't spend too long, of course, talking about what's all of this stuff. This is fundamentally, in summary, what controls the microscopic system that is the quantum computer, which is this inside this little golden disk in the bottom. That all the rest is control systems, and actually the chip is within that golden disk that you see here on the right. That is really the core of the quantum computer. So it's a very small system, as you would have expected, but of course the control system isn't that small. This is only one way of building quantum computers. It's the superconductive approach to quantum computing. That's the one we use. That's the one that IBM is using. That's the one that Google is using. This is far from being the only possibility. There's intense research on many other possibilities. They're listed here: trap ions, photonics, etc. And I'm only mentioning 2 of the players involved in the hardware effort. This is far from being a complete list. It's a much longer list, even just at the hardware level. The last thing I would say is, I think as a business user now, the natural question is, how do I program the stuff that's in the cylinder? Now, it is easier, fortunately, than you might think, because there is, and this is again our software stack, there are equivalent software stacks, but what actually is given to the end user is development environments accessible to the clouds that are pretty much very similar to what you would be using for classical computing. The thing that isn't similar, and I think that this is an important point to stress, is the fact that quantum algorithms are very different in nature, and even if the programming environment is similar, for someone to be able to write a quantum algorithm, there is, of course, a bit of learning and significant differences that need to be understood. And even understanding the applicability on a business problem isn't trivial, just because, again, the logic of these algorithms is profoundly different. So the effort on hardware has been significant, there's been great progress, but equally, I would say that the effort on algorithms and applications in the working, in fact, with businesses and in trying to understand what the applications are, it's been equally important. And I think on this aspect, this is how QxBranch, so on the algorithms and application with business users. This is how, at the center of QxBranch proposition. And maybe I'll let Paul talk a bit about how, in fact, the project started and how it developed over the years.
Yeah, that's right. I wonder if we can skip ahead just real quick, Marco.
Sure.
And I will make a comment, and then you can correct it or add to it a little bit, because I think at this point we should talk about what are the types of problems that quantum computers are good to solve, just from a formal perspective. And I haven't been at Rigetti QxBranch in about 2 years, so I'm a little bit rusty on this. But what we were looking for when we were working with a number of organizations are classes of problems that take advantage of quantum behaviors that allow us to interrogate a massive number of incredibly complex and intertwined numbers at once. So one of the classic examples of a problem that you can address very well, not necessarily solve with a quantum computer, is something like a traveling salesman problem or a combinatorial optimization problem. There's many classes of problems where you need to evaluate what's the best combination of a large number or even a small number of variables. And in those cases, there's some algorithms that you can use to create some shortcuts. But for the most part, there's no mathematically efficient way to solve those problems except by brute force. And the law of exponents means that some very practical day-to-day problems can become intractable incredibly quickly. And so, the traveling salesman, I'm sure those of you that have any computer science would be very familiar with this. Those of you that don't might find this a little bit interesting, or maybe you've learned it in another way. It's a common problem. But if I have 50 packages to deliver around London, finding the quickest route to do that is essentially, I actually usually get this wrong. It's like n to the 50, right? Marco, please correct that. Is it?
Yeah, it's exponential in the nodes or in the cities or in the stops.
Yeah, but it's not n to the 50. It's like 2n to the 50 or something like that.
Yeah, well, I think it's the 50 appears as the exponent, so it would be.
That's right. So if you have 50 nodes, it's an exponent of 50 to basically, which means that if you add one more stop, you've now made the problem an order of magnitude more difficult. So it will take 10 times longer to run that problem. And something like 50 or 100 packages to deliver, that is a very, very practical problem. And you can run into these types of problems all the time in any type of AI environment where you're looking at a system that has 50 variables is not a lot of variables for an AI system. We regularly look at those in the thousands. And so being able to look at what are all the combinations of behaviors between all those variables, that's a problem that with even the most powerful computers, the amount of time it would take to solve that efficiently is in the billions of years. And so you can kind of run into these problems all the time. So what we were looking for, those types of combinatorial optimization problems. We're also looking at, there's another class of problems that's gonna skip my mind. So I'll come back to that. But basically say that what you're looking for is not necessarily problems that are really big or sort of seem very complex. They can often be very practical and very day-to-day. But what quantum computing allows you to do is it allows you to unlock all of those different combinations very, very quickly. And it does it by simulating that as a physical energy system rather than as a series of numbers, and then finding energy states that correspond to optimum values there. So it's more like finding the lowest point in a valley than it is like first calculating every point in that valley and then comparing those numbers. So it can be a very efficient way to solve certain types of problems. We'll come back to this. So the history of how we set up QxBranch, and I'll tell some examples along the way, was kind of a little bit unusual. I was working in Washington, D.C., as I mentioned, doing a bunch of work with NASA, with the U.S. military. One of my clients was one of the top systems engineering firms in Australia. They had just designed the new Australian submarine program. Lockheed Martin, who had just purchased the first ever commercial quantum computer, a D-Wave, which is a different architecture than Rigetti, Lockheed Martin came to them and said, hey, we have this new toy. Do you guys want to play around with it? And they said, I have no idea what quantum computers are, but of course we want to play around with this. We ended up getting some interesting results on it, enough to decide, let's kind of start a company around this and let's start playing around and see what we can do. And we had some early conversations in the US military community and the US intelligence community around some proof of concepts around analyzing, satellite data and doing some other types of complex analysis. Strangely, or not strangely, but I guess unexpectedly, we ended up getting a bunch of information, a bunch of inbound interest from asset management firms. So we started the company, we raised about $1 million into it. We started working in Hong Kong with a bunch of financial institutions in Hong Kong, as well as based in New York and in London. And what we would do with them is a type of consulting engagement where we would do something like an audit of all of their complex systems. So we would go through these companies, we would do 30, 40 interviews. We would talk to all their main quants. We would brief them on what quantum computing can do. They would brief us on some of their models, some of the Monte Carlo analysis that they were doing, some of the forecasting that they were doing, some of the asset pricing, and we'd look and kind of pull apart all those models and find like here is a combinatorial optimization problem, or here's another type of problem that you could solve with quantum. We generally found that those types of problems, they were using a lot of simplifying assumptions that they would love to unlock, but they just kind of knew that they couldn't solve the problem the way that they wanted to solve it. And then once we found a couple, we would down select and we would do proof of concepts to start to build the algorithms. Once you build the algorithms, you can predict how long it's going to take until quantum computers are able to run that problem. So there's certain problems that need like a different size of quantum computer. I think the current machines right now have something like 70 qubits. There's certain problems that you can run on that. They're roughly equivalent to the best supercomputers right now. There's some problems that you need 1 million or 1 billion qubits, and so you can project out when that will actually happen. And then the output of that is like a technology strategy that says, here's how we're going to position for quantum computing in the future. We know that this application is going to be ready to run in roughly 4 years, because that's when the hardware is going to be there. We know that that application is going to generate $10 in revenue. We know that it's going to take 2 years to build the software. We know it's going to take a year to procure the hardware or whatever. So you can predict out exactly when you need to start spending money on that in order to be executing that particular problem at a particular date.
Paul, just jumping in there. So that makes absolute sense for the approach to a roadmap. But how did you and how do you predict the sort of the growth of available qubits and the relative cost? Is that magic, or is there a science to it?
Well, it's a good question. It's so it is possible to predict. I'm pausing because it's such an interesting question. The answer to the question is that you can largely predict this stuff. I did this study many years ago with the U.S. intelligence community. We looked at tens of thousands of technology forecasts over a 30-year period, and then validated how accurate each of them was, and then kind of analyzed the different methodologies that were used to try to figure out what's the best way of forecasting technology. And strangely, one of the best ways to do it, though it's not foolproof, one of the best ways to do it is just drawing a trend line. And the reason for that is that all these companies aggregated together have a particular type of research agenda. They're obeying certain KPIs. They're working very hard to meet those. They're changing their budgets to meet those. And they're generally successful with some caveats, like certain things do slip. When you ask experts who understand that problem very intimately, how well they know that problem inhibits their imagination from being able to conceive of that problem ever being solved, and they will tend to overestimate how long that problem will be solved. So with something like quantum computing, you need to look at the technical side of things and understand the challenges, but you also really need to look at the market pull and understand that the forces going into solving those problems are variable, and they can get ramped up And if there are big market opportunities looming, then that will draw different types of investment and R&D funding that will go into solving those problems. So certainly the the roadmap to quantum computing has slipped a little bit compared to what we thought it was going to be 5 years ago. But at the same time, some of the accomplishments that are happening today are, we just wouldn't have been able to imagine a couple of years ago. Yep. So that's the idea. There's one other thing that QBranch was really heavily working on, which Marco mentioned, which is development environment. So in the early days, to be able to design algorithms and to write software for the computer, there's a lot of specialized skills that are required. In any computing environment, there's a number of abstraction layers that are built on top of the hardware and on top of each other, so that you can get to the point where you can just kind of drag and drop code, and anyone can do basic stuff. Certainly you still need great programmers to do complex things. But QBranch was very much involved in building development environments and building algorithm libraries and software libraries that would make it very easy for individuals to get on into a new environment and start writing quantum software in normal languages like MATLAB and Python, and to be able to use those computers and get pretty good results. Do you want to talk maybe, Marco, about your work at Rigetti and how that sort of changed?
Yeah, sure.
I would also say, if there are any questions that want to roll in from the crowd rather than us blowing through this, we're more than.
Yeah, please just put them in the chat.
Sure. Yeah, I think in terms of application and algorithms, I think the work as Rigetti hasn't changed greatly. I think there is still, so quantum computing is difficult, and not just difficult from an engineering perspective, but again, it requires like a mix of skills that is quite sophisticated, because again, fundamental algorithms require researchers often from academia, and then you've got you need the software development skills, and then you actually need to be working closely with the business users. Ultimately, they understand the real needs. So I think in terms of application algorithms, the effort at Rigetti isn't too different, and it is my my area of interest in particular. And maybe I'll expand a little bit on use cases. I've got a couple of slides, and I can show a bit more on use cases. Of course, from a Rigetti perspective, it's a full stack play as opposed to just algorithms and applications. In a way, having all aspects that go from manufacturing of chips to actually writing end user application, it is useful, because I think that there is a feedback that goes all the way from useful real world applications to even how possibly chips are designed or how a quantum computer is built, and sort of vice versa. I mean, understanding some of the things that happen in the box is actually useful to understand what possibilities practically someone has in terms of algorithms. I will actually, let me talk a bit more about use cases. I'm going to share my screen again. Expand, I think, on the optimization use case that Paul has mentioned, which is a great use case. And I think I'm going to go straight to actually this slide. And this is actually specific to financial services. This was a slide that has been built over time. In fact, we built based on, I think this is all based on public announcements. We've had interaction with several of these players. This is financial services with a bit of a biased view towards investment banking. I think investment banks have been the most active, at least in the financial services industry, in engaging with the quantum computing community and trying to understand, in fact, what the possibilities are. And that trying to understand goes for the most part beyond just reading a little bit of literature and seeing where the industry is at. There is direct involvement of some of the banks in some of the startups. The several banks, actually, I'll show it on the next slide, and I'll come back to use cases. Most banks, and this is updated as of November of last year, they've actually published work in quantum computing. And it goes from highly theoretical quantum computing work as, for example, the piece that Goldman Sachs had written. This is a purely quantum computing paper, and two others that are a bit actually more specific and applied to financial services problems. So there's been significant engagement, at least from the investment banks. And this is, I think, an acknowledgement of the fact that the potential around certain problems is significant, and they don't want to fall back. I think, going back to the use cases, I think the use case, the example that Paul has mentioned on the combinatorial problem, we have an example of the exact same combinatorial problem, which is portfolio management problems. In like a classical portfolio management formulation, it is a combinatorial problem. Now, beyond optimization, and of course, optimization is an important class of problems. We are doing now a lot of work, and in particular with one partner, which is Standard Chartered, on machine learning. It's actually called quantum machine learning, but it is nothing but the use of a quantum computer on traditional machine learning problems. So we look at discriminative models, we look at reinforcement learning, and right now, at present, we are focusing on generative models. And I'll explain what that is, because technically it isn't anything too complicated. Then, of course, the algorithms and the technicality is quite a bit more. But so generative models are fundamentally models that allow the creation of synthetic data. It's data that doesn't truly exist, but that mirrors some distribution. You might have seen, for example, the synthetic faces. So faces that actually look like real people, but they are just computer generated. They're not people that exist. So that's an example of synthetic data. Synthetic data is very powerful for a number of reasons. And in the case, of course, with Standard Chartered, we're talking about financial synthetic data. It is powerful for, again, there is an aspect of many systems are hungry for data, and Monte Carlo methods and just scenarios simulation require data. We've shown that actually even other machine learning models, for example, for predictive systems, train on the real available data set perform worse than if trained on the real data set plus additional data created artificially. And so the synthetic data can also serve can boost other machine learning models, and as simple as really predictive, so classifiers, predictive models. And then I think the other important aspect is data anonymization. Now, data anonymization, and the problems around privacy is it's hard to actually maintain to cleanse the data and try to maintain data that resembles true data, removing the sensitive information. And very often it is even hard to have guarantees that that information has been removed successfully. Now, with synthetic data, that problem doesn't exist. And that is because it is by definition data that doesn't exist in the real world. So I hope that gives an idea, and I'm happy to take questions, but that gives an idea of the sort of classes of things that we look at. Machine learning and optimizations are no doubt core classes of problems that we are currently trying to tackle with the quantum computing method.
Thanks, Marco, for that. There's a couple of questions that have come in on the insurance side of financial services. So yeah, if we can touch on them. So one, well, I guess this is more than just insurance, but generally it says here from Craig, with Paul's current focus on cyber risk, is quantum in hands of bad actors a risk that's being well managed? So I guess there's a number of questions in there. One is, is there a risk? And two, how's it being managed? Paul, do you want to have a go at that one?
Yeah, certainly. So everything that we're talking about is commercial quantum computing. And most of these companies that are active here, Rigetti, IBM, Intel, they are working with systems that they use commercially. They also use them for some government and some defense applications. It is widely theorized that there are systems that different governments have developed that are not commercial, that may have different sets of capabilities that may be more evolved than the capabilities that are in the commercial world. And you can, if you look very, very closely at certain, trade, different types of defense policies and, technology trades happening between companies, you can see some hints that something like that may be happening, but there's really not a lot of public information on that. So it's kind of assumed that those systems exist. They certainly exist in, with the likes of Russia and China. I would imagine that the US is working on some kind of independent capability, but I have no ability to assess that. When it comes to the trade controls on quantum computing, those have not yet been implemented with a lot of severity, partially because we're very far from quantum computing being able to break encryption. That's probably about that will be one of the last problems that that's not going to be one of the first problems that quantum computers are really used for, because it requires a pretty large quantum computer to be able to do that. So there's not a huge amount of control on this technology right now, but it's expected that the control on this tech will be similar to the environment that we see with space technology, and maybe a little bit more stringent.
And so building on that, do you have a view of the concept of sort of harvest today, decode tomorrow? So
yeah.
The data gets stolen, but 5 or 10 years hence it gets decrypted.
Yeah. Yeah, that's something that is a potential very big issue in insurance and reinsurance, and it's also something that's an issue, obviously, with in national security. And I guess for those of you on the call, the idea is that there's a lot of data out there that's encrypted. In some cases, not all cases, but in some cases, that data may be less well protected because it's encrypted, because the view is that it can't be broken. But we know that there is a future that will exist within our lifetimes, that whereby most of that data will be very easy to de-encrypt. And so there's been strategies observed by some nation states to hoover up as much of that information as possible, knowing that someday they'll be able to just have a free run at all of it.
Thank you. Another question on the insurance side we've had, and this links a bit to the point about what a combinatorial optimization questions and analysis of large numbers and things. The modeling of the impact of hurricanes and earthquakes and wildfires is obviously at the heart of managing risk in insurance. It's a very practical problem today that's dealt with by computers. Do you have a view as to whether quantum computing will drive a step change there, or it's a problem that's not necessarily relevant for quantum computing approaches?
Yeah, I think that's a very relevant problem. So a couple of years ago, I was at a NASA Earth Science conference, and I heard a great stat, whether or not it's true or still true, it probably is, that there's, I think, 17 orders of magnitude of data in the atmosphere, and that we can analyze 5 of those right now. And we tend to gain 1 order of magnitude every decade. And so I don't think that it would be accurate to say that quantum computing will immediately allow us to create a very accurate simulation of the atmosphere, but it may accelerate that process a little bit, maybe give us 1 or 2 orders of magnitude more, and allow us to predict things with a lot more certainty. Weather forecasting in general is kind of this quiet success story. I think that right now a 5-day forecast is as accurate as a 2-day forecast used to be in the late 80s or early 90s. So we are getting much better at this stuff. With insurance, you're looking not really at weather forecasting, but climate forecasting, which is different. You're making 12-month predictions. And that's something I don't have any fun stats on that, but certainly the ability to simulate that will increase similarly.
Okay, thank you. There's a few quick fire questions, sort of more on the technology side. Let's without delving too deep, it would be good to cover those. So Shannon's asked, are there other metrics aside from quantum volume that can help compare current maturity levels of hardware or software? Marco, do you want to have a go at that?
Reason I think it is an interesting metric introduced by IBM is because it really tries to summarize in a single number how good a quantum computer is. It is an effective metric. Now, the in general, I think that there aren't any other single number metrics that are used, but there are a few things that are fundamental, and that is the number of qubits, and that is the fidelities. There are other things about coherence, and then in some cases, actually, the evaluation of how good a quantum computer is specific to a problem. So there is a method that is used for optimization, and there are two parameters that actually matter. One is sort of like represents the number of cycles, and the other one sort of, again, the qubits. In that case, so the bigger the product of the two you can run the algorithm successfully on, the better. So I would say yes, but they become a bit more detailed than this quantum volume, which IBM has introduced.
Okay, thank you. And sort of building off that, I guess, as we try and almost visualize these ever more powerful quantum chips, the actual production technology as we move up the number of qubits, is that sort of starting to require billion-dollar factories as we have for classical microchips, or is the actual production cost not the challenge? It's just more the management of noise and things in higher volume qubits.
No, it isn't the production as it isn't a scale problem. I think the number of chips or number of computers, at least for now, I think again it's an engineering challenge. Building machines with more qubits and with less noise.
Yeah, and it's an interesting question that kind of gets into the nature of path dependency in technology. I would say that there's been a focus more on technologies that can be developed with existing fabs and existing fab technology, precisely because the scale to do that type of thing exists. So, an example to partially address one of the questions, above, Microsoft has pursued this very scalable but very idealized version of what a quantum computer can be based on a subatomic particle that wasn't proven to exist when they started developing the computer. And that was kind of like looking for theoretical scale. Other companies and have since discovered it. Some other companies have said, you know what, to really scale this thing, we need to work in a silicon environment because we have the existing fabs, we know how to use it, and we know what scale looks like there. So let's focus our R&D effort in an area that maybe is a little bit more challenging from an R&D standpoint, but is much less challenging from a scale standpoint. So the two things are related in a dynamic.
Thank you. There's a question from Robert about language that's used, and I might expand that a bit to conceptually, if one thinking I have a company that can benefit from this, is there a need to sort of cross your fingers and pick the right type of quantum technology and the right supplier? Because if they're the wrong one, then you're starting from scratch with another one. Or, inherently, if you're able to define the problem that's suitable for solving by a quantum computer, then you can just jump between suppliers and jump between hardware.
Yeah, so the latter for the most part. So when I say for the most part, there are two main quantum computational models still available today. There is it's called quantum adiabatic, and then the general, which is what Rigetti does and Google, etc. Within the general, even if the devices are different, and even if Microsoft, I've seen here in the chat, is trying to build something physically completely different, the logical, the programs are identical, and there are variation as the languages, but the logic is the same. And in fact, there are even now cloud providers. AWS is one, and we are on AWS as Rigetti, offering the backend services. That are already sort of putting together different backends with a common user interface and with a common logic exposed to the users. So no need, I think, for an end user to worry about picking one hardware or the other.
Yeah. Okay. There's a couple of questions building up at the end, and there's some. We've had this discussion in many previous of our webinars, which is around. Is there a potential inflection point where someone may say, okay, investing in the power of quantum computing, albeit very expensively, is going to give us a disproportionate advantage in, say, high frequency trading or crypto mining or something. And the moment they do it, there will just be a sort of complete shift to how that market plays out. I don't know if either of you have a view on that and sort of when it may happen and which markets it might affect.
You want me to take it, Paul, or?
I would be curious about your view. I can give a quick answer as well afterwards.
Yeah. So I think for specific problems, again, assuming that things will play out as we imagine now, our ability to resolve the problem with a quantum computer compared to classical techniques will make a significant difference. And so the ones that have access to the tool and will be making use of the tool would have a significant competitive advantage compared to the ones that don't. Now, I don't imagine sort of a big bang event when all of a sudden, for a specific algorithm, someone all of a sudden will start running this with a quantum computer and nobody else does, and that will be the undisputed leader on that specific computation, whatever the case is for. I think again there's been a gradual involvement of firms in industries that might be affected. I think there is clarity, more or less, at least now, on the sort of hardware available and algorithms available. And I would imagine even the first cases of the so-called quantum advantage, where you run something on a quantum computer that you cannot do classically, to be initially small advantages. And then I think that we will hopefully see that the exponential growth and the separation from classical becoming substantial. But I don't see it as, I don't see it as a big bang event that will take everyone by surprise.
Thank you, Paul.
Yeah, I mean, that's roughly what I was going to say. I think that it's, most of high frequency trading actually doesn't even use any machine learning. It's just kind of trend following, and they're very simple rule-based algorithms. There is more machine learning trading in the stock market. It's kind of based on fundamentals, and it's based on reading the news. And it's one of kind of the main triggers that then triggers all those other algorithms. I think the stock markets globally have been moving in a very weird direction in the last 10 years. The days of individuals deciding that this company is a good company and buying it profitably are over. It's most of the traffic on, between passive investors and, active machine-based investors. The stock market has very weird dynamics, and this will be an evolutionary approach to that. But already the ability to analyze fundamentals is not particularly relevant today the way it was, back in the day. So it'll be strange how it works. I don't think that it's going to change the nature of it. And I think that if you're looking for really weird, strange behavior that you would like to unpack and understand, I think it's a very rich area to look at today, just given the tech that's in the market today.
Perfect. And that actually triggered a thought that hasn't been raised today, but was asked before. And I think it's just helpful if people haven't heard it before. There was a question, and this was triggered by seeing someone mention crypto mining, that, is quantum computing going to drive global warming because somehow the machines used vast quantities of power? Now, we've been told previously the answer is no, but it would be good just to hear that again, maybe from Marco. Those little chips sitting at the bottom of your hyper-cooled units are presumably not going to destroy the planet.
Yeah, and of course, the quantum computers are efficient compared to a classical system, and very efficient compared to a classical system for the problems that quantum computers are good at. So no doubt that if we were to use a quantum computer for a task that is extremely energy, that consumes a lot of energy, and it is a task that quantum computer is good at, then yes, it will be a lot better from an energy consumption perspective. Then, of course, depending on how many quantum computers we'll have and to what scale, they still, of course, burn energy. And so, but it is true that they are, for specific tasks, they don't scale exponentially in energy consumption as classic computers do for certain tasks as they become larger.
Fine. I think to wrap up, Craig's decided to give us the most convoluted question we've ever had. So Paul, I'll probably let you even extrapolate. I presume we're saying quantum as a service, but then I've no idea what he means by DBAAS. Do you want to have a go at that one, both at interpreting and answering it?
I think I don't know that quantum. So, Marco, correct me if I'm wrong, but quantum computing functions, when you run them, for the most part, they happen in a set amount of time. And it's not as unpredictable as it is, when we run a lot of machine learning functions, we often can't predict when that thing's going to stop, and maybe there's a loop in it and we have to shut it off after a couple of days. Quantum computing just has very, very different dynamics where it just kind of hits the problem and it gives you the answers. So I think that it's actually much, much more predictable.
Yeah. So I see. So the one aspect I think is because even now, for example, going through AWS, you could actually buy quantum compute time to our system, but to at least two other systems that are connected, you could and the sort of cost to the customer is just the time allocated and the use of the resources. So it wouldn't be so, and there are some algorithms that actually take a bit of time because there is an exchange between quantum and classical, and it goes on for a little bit. So certain things do occupy us a lot of time, and it's pretty much like using classical resources. I think the variability and the interesting dynamic on price, I think it will come when we start seeing the case of quantum advantage, and whether at that point the quantum computing resource becomes a precious resource. So all of a sudden we get into a situation where there's more demand than supply. I don't know if we'll get there, or in fact we'll be prepared and we'll have sufficient quantum computers around to serve that demand. But for now, I suppose nobody really is using quantum computers to resolve production problems, and so that is very different from when there will be a return and actually creating business value by running algorithms. So I think we'll see an interesting dynamic on price then. For now, it is literally just like a cloud resource, very much like other resources you can buy through cloud providers.
Brilliant. Well, thank you. I think that's a perfect point to end. So just to wrap up, we said we'd keep things to an hour, and I think we've so before saying thank you, I just want to remind those who've joined that obviously there's the usual social media channels to follow us, and the usual ways to find out what's next. We have got a regular Quantum London Stammtisch happening next Thursday of next week, and as with previous ones, what we'll do is we'll discuss some of what we have talked about in tonight's webinar, so look forward to people joining that. Please follow us on the various channels. We'll have a copy of this video available in the next day or so, and a write-up of the key points. So really it just remains from Em and from myself to say thank you, Marco, thank you, Paul. We've appreciated your insight, the education, and tackling those various different questions. So thank you very much.
And if you want to reach out to either of us, we're more than happy to chat.
Thank you for having us.
Thank you. Good night, everyone.
Thank you. Thank you.
Bye.
Bye-bye. Bye-bye.